Welcome to this lecture on least squares method for curve fitting. We will present a geometric interpretation. We will illustrate with an example. Let's take this non-square system. These equations are in the form Ax equals b with A as given here, x has the unknowns k and c, b is given here. A and b are usually experimentally obtained data. It is a system of three equations in two unknowns. We will also refer to this as a tall system. As a matter of fact, I used this terminology in the previous videos. How does one solve this? Consider the following non-square system, a tall system. Aij and bk are usually obtained experimentally. x1 and x2 are usually model parameters. Need to find x1 and x2 from the above equations. How do you interpret these equations? System of three equations in two unknowns. It is a overdetermined system. What is the geometric meaning of such a system? We will present one interpretation of this system. We can consider this as three lines intersecting at a point, but how often can this happen? So we go for another interpretation. We can write this as follows: the first column multiplied by x1, the second column multiplied by x2. You can multiply these two and verify that you indeed get this system. Once again, what is the geometric meaning? So let's start with the system we had in the previous slide. A1 and A2, this is A1 and this is A2, make a two-dimensional space, a plane. Left hand side is in a two-dimensional space, a plane. For example, this denotes one direction, this denotes another direction. So a linear combination of these two will be in a plane, whereas B is a three-dimensional vector. And remember, these A's and B's are obtained experimentally. So what do we have here? We have a plane here described by two vectors, but on the right hand side we have a three-dimensional vector. It can be solved only for a very special case of B, namely for a particular set of B that will be present on this plane. In general, however, this B cannot be constrained to this plane. We can represent this geometrically in the next slide. Here is the A plane, the plane that we had on the previous slide, and this is a three-dimensional vector that lies outside this plane. So I call this the A plane, all combinations of A1 and A2 vectors. B lies outside this plane. So can we satisfy Ax equals b? Exactly. Okay, once again let us consider this. Ax equals b. Ax is a two-dimensional vector, it lies in the A plane. B is a three-dimensional vector, lies outside this plane. So we conclude that Ax equals b has no solution. The question is there an approximate solution? What is the best solution possible under this situation? We will present the idea geometrically here. Approximate x with x0 lying on this plane. Remember, we want to say Ax equals b, but b is lying outside. So we want to replace B with Ax naught. If B can be replaced by a vector of this type which is present in this plane, then we can solve the system. So this vector should be closest to this B. Closest means what? Closest means that it is nearest. So we drop a perpendicular from here and you take this endpoint and take this vector, that will be the vector closest to this B vector. So we say E is perpendicular to the A plane. This E, the error, is perpendicular to this A plane. If we do this, then this vector is the closest to this B which lies outside this plane. Now the question is, how does the smallest E help calculate x naught? How to make E perpendicular to the A plane? Make A perpendicular to every column of A. What is the A plane? It is obtained by taking linear combinations of the columns of A. So you make this E perpendicular to every column of A, so that E will be perpendicular to the whole of A plane. Alright. So how do we do this? How do we make this perpendicular to every column of A? We make the inner product of E and every column of A equals 0. We do that here in this slide. Inner product of E and every column of A equals 0, but A equals A1, A2, it has two columns, and E is equal to Ax naught minus B. We can see it in this picture. So we say that inner product of this A1, the first column of A1, the first column of A, and the error vector Ax naught minus B equals 0. In other words, A1 transpose into Ax naught minus B equals 0. Remember, A1 is a column. Here I take a transpose. As a result, this is a row vector and this is a column vector. So I write it as row into column. This is for the first column. Similarly, I write it for the second column. So I get A2 transpose into Ax naught minus B equals 0. Remember, these are row into column. So from the previous slide, I get these two equations and I can stack them up. This is a row. So this is first row, this is the second row. Together it makes a matrix, and hence I can write this as A transpose. This is nothing but A transpose, easy to see, and we get this matrix equation. So we get, on multiplying out, AT into Ax naught equals AT into B. How do we solve this? We solve this directly using LU decomposition or any other numerically stable method that is available. In very large systems, there exist special methods, especially for sparse systems. We use one of those methods to solve this equation. When you solve it using LU decomposition, you can show that it is of the order of n cube operations. In sparse systems, the number of operations required could be lot less. One never finds the inverse, however. This is a very important observation. You should solve this equation directly. You should never find the inverse and then multiply this out. But we mathematically write this as follows. Whenever it is written like this, remember, you should always go back to this form, that is equation form, and solve this using LU decomposition or iterative methods. but for small systems it is okay to invert. In the example that we considered, we will arrive at a 2 by 2 system for this ATA, and hence we will invert and then solve this. In a large system, however, we have to solve this equation directly. So the solution to Ax equals b is given here. It is denoted like this. Okay, can I always find this inverse? In other words, can I always solve a system of this type Ax equals b? Can I always solve a system of this type ATA x naught equals ATB? So we say that inverse of ATA should exist. Recall that A is of this type. In this particular example, it is a 3 by 2 matrix. So ATA is a 2 by 2 matrix. When will ATA be singular? When even 2 out of 3 equations are not independent. What I mean is, remember that we actually started with more number of equations than required. We have only 2 unknowns, but we got 3 equations. So one will assume that possibly you have enough information, but it is possible that even though we have 3 equations, it still does not have sufficient information. When will this happen? For example, we write the same equation 3 times. Then obviously we do not have enough information, but we are trying to cheat. So this is what I mean by we cannot cheat by mathematical jugglery. Let us go back to the example we presented, the numerical example. We had this A, X and B variables, 3 equations in 2 unknowns. So you can calculate ATA as given here. We find the inverse. Because it is a small system, we can invert it and we can substitute in this expression and obtain this result, and this is the vector Kc. Why do we call it least squares minimization? Because we took the sum of squares of error and this results in 2 norm squared. The shortest distance in 2 norm is obtained by taking perpendicular. Remember, we dropped a perpendicular to identify the closest vector. This is the smallest error in 2 norm, and we took 2 norm because we took squares of errors. We did not take absolute values, we did not take the largest value, but we took the squared error. That is the reason why this is called least squares minimization. To conclude, the solution to a tall matrix is obtained by a projection. It is solved using an equation of the form Px equals C, and of course I would like to point out again, this is an extremely important observation, especially in large systems. Do not ever try to invert the matrix P. P of course in our case is ATA. You solve this directly. Of course for small systems it is okay to invert, just like we did in this presentation. With this, we have come to the end of this presentation. We would use this in a subsequent video where we will arrive at the GPC law. Thanks for joining. Goodbye.